I started developing Rockyfor3D in my thesis, so we're talking 1998. Then I had simple GIS approaches based on articles I read at that time. When I came to the team of Fred Berger in Grenoble, we had the chance in an EU project to really observe a lot of rock falls by creating them ourselves. This is showing what we did. We were on a slope close to Alpe d'Huez, and we had there a slope with the same geomorphology, the same steepness, quite linear, but on one sector we had a avalanche track in a forest, and next to it was a forest with about 270, I think, trees per hectare, so not very dense, but also not really open, and quite some big trees, beeches and white firs, and some spruce trees. And we threw hundreds of rock in that avalanche couloir and filmed those, and we did the same thing in the area, the sector next to it in the forest. So for that, we had a caterpillar during that project, and what we got from that is nice videos of around cubic meter blocks going down the slope. This is that avalanche track. You see there are not so many trees in there. It was more or less 10 meters wide, between 35 and 40 degrees steep. And some rocks were coming down like this, just what we usually expect when we think about rockfall. Some were jumping just stochastically in the middle of that slope and then flew through the air like 50 meters long rebounds and 8 meters high. So think about, we let those rocks go from that forest road up there. We had a sector of 250 meters going down with 5 cameras, could cover the whole slope. Old cameras at today, not so fast. We had 1/25 second we had an image. So with that, it was barely sufficient to see how rocks impact the tree and calculate the velocities from that. Nowadays, there are better apparatus to do so. But some rocks, like the following one, they choose not to jump and they stay very close to the slope surface. I just have to organize the sound here. So you see, they don't jump up, they are very tangential to the slope, and they have enormous velocities. So this is about 100 meters after releasing that rock from the forest road. This is not falling from a cliff. And there you see velocities of 135 kilometers an hour. So we observed velocities up to 32, 33 meters per second here on that slope. So once more this one, because that is interesting. So if you throw all these natural rocks, you see an enormous variation between the trajectories, the jump heights, the velocities, just from the same point going down in a narrow avalanche couloir, and still seeing so much variation. So that was the important one. So if we analyze then afterwards the images, we got images like this. So you see the acceleration in the air. I mean, the distance between every 1/25 second becoming larger. We knew them from the ground how much distance is, and we could calculate velocities. In the forest, we did the same thing. We went down the slope, we recorded all the damages, we recorded the trajectories, not with laser scanning, just a very old-fashioned forest approach, looking which direction and the distance, and then we had it later in our GIS. We're talking here the year 2002 and 2003. So in the forest, voila, our objective was indeed to have impacts on trees where the trees were then, so to say, cut, so that the maximum energy could be calculated from the total kinetic energy before the tree impact and right after. I mean, as I said before, our cameras were not so fantastic, and we didn't know in the forest which tree would be impacted. So we were happy if we had images on impacts that we could really use to analyze the energy dissipative effect of trees. To give you some examples of those, voila, this was what we were really looking for. So you see, we had with these cubic meter rocks in general, I mean, the mean volume was 0.84 cubic meters. The smallest ones were 0.5. The biggest ones were up to 1.7 cubic meter. If such a rock of 1 cubic meter with about 24 meters per second impacts a white fir like this, 58 centimeters, the rock goes literally through the stem. But this was excellent. This allowed us to then calculate how much energy can be dissipated by such a tree. So from that work, I won't spend too long on this. We also were able to analyze what is the relation between the travel distance of a block and the encountered basal area in a forest. I won't explain this. This is not the objective of today to talk a lot about forest, but it's an important factor in the model, but not the only one. But you can see there we found some nice relationships, how denser the forest, and also quantifying that, how much you need to have the average stopping distance on a linear similar slope like this. So how does this Rockyfor model function? We start with 0.5 meter per second, and the rock goes down in 45 degrees. So you have a horizontal velocity in the direction of the aspect of the starting cell. So we calculate just like a normal GIS with the orientation of a start cell, and then we throw the rock with 0.5 meter per second in horizontal and vertical down direction. So the rock goes down. And then we calculate with a simple Newton approach, a parable through the air, where the rock is at the end of that cell. Is it below the cell? Then we calculate back where the impact would be. If it's still in the air, we go to the next cell, but not before checking is there a possible net or a tree impact in the cell. Well, we do that all the time. If it's coming on the ground in a cell, we calculate a rebound, which is the complicated thing in rockfall modeling, how much energy is lost during a rebound on the ground. And after the rebound, you're flying again. And then you can see in that flight, am I exiting the cell or am I still in the same cell? If yes, then there's a next rebound or an impact on a tree or on a net. And you do that until, in the end, the rock has a velocity less than 0.1 meter per second as a resultant. So this is why the model is so rapid. You don't have to do a iteration over time looking of if your 3D form is connecting or contacting the slope surface, which make it relatively analytic, the model, and that makes it fast. I said this before, we use the parabola that has been invented by Newton after having an apple on his head or not, nobody really knows. And as I said, what is really the complicated thing is the rebound. What's happening there? We don't exactly know. I mean, SLF did some really nice experimentation with Axel Volkwijn where they equipped rocks, concrete rocks, with sensors, seeing how much energy is lost, but still what is happening in the underground, you can only see that after looking into those rebound craters, impact craters. There you have an idea how much was the soil compressed, what was 1 meter below the surface, which I never saw when I was in the field mapping. I mean, now this is a great case of a rockfall in Valais, in Teche, where a rock came down. I don't have the exact distance in my head. I think it was about 500 meters through a forest, coming down on a road, and there's a small dam separating the road from the golf court. And on that dam was a big impact, and it's not so clear if that rock split it into two or it remained the same, but there's one rock lying on the dam and the other of about 30 cubic meters, I remember well, was the total volume. Flew through the air, landed about 30 meters after the dam on the golf court, making this impact, and then out of that impact crater, and then stopped. So what was its rotational velocity of the block? Which penetration side of this block came into the golf course at the time of the impact? What was its exact block size and form? And what was the exact underground composition? I mean, the topsoil is really nice for the golf, the green, of course, but this is the first 20 to 30 centimeters, the black one. And below that, well, we have the river depositing alluvial material. It's difficult to say before the rock comes down how this is going to react to an impact. So this is the complicated thing. And we talk a lot about block size and form when we talk about rockfall modeling, because probably you all agree with me, nobody has seen a rock coming down a slope that became bigger and bigger. They tend to become smaller and smaller, and sometimes they're round, then they split into two, then you have two disc-shaped rocks that fragments again, losing parts, that gets rounder, etc. So it's changing all the time on its way down, which makes it so complicated. I have a nice video on that a bit later. So therefore, we use a lot of stochastic approaches here that are going to take your parameters that you mapped in the field, together with a physical approach of penetration in the ground, to calculate how much energy is lost during the impact and the scarring here on the ground. So that's what we call it, a Monte Carlo simulation. Monte Carlo simulation is the good old word for doing a lot of repetitions, where every time you start to vary your parameters with a given small distribution. This can be a normal distribution or an equal distribution. This can all be defined. As you saw in that image, impact depth is important. We, since a long time, we have this algorithm of Pichler. Pichler was an Austrian guy of the Technical University of Vienna. And what they did is, with a crane, they lifted big rocks and they dropped them. There's somebody unmuted. And dropped them on different materials, like a building site with only fine material, and then they measured the penetration depth. And I tested at that time, and I never changed it since. I tested a Japanese and an American algorithm, and the Pichler was the only one that had, for me, realistic impact depth that I observed in the terrain, and I could also then recalculate. So that's what we took. So we calculate with the assumption that the rock is round here. So even if you say it's a rectangular rock, there's a factor giving the nose factor. That's how the block is shaped. And there we always set it to a round block. And with that, we calculate, based on the underground material, the total impact energy. But we'll have to think. The moment of inertia, the compressibility of the soil, we calculate how much is the penetration depth. And we add that to the roughness that you mapped in the field, and that gives us the total roughness or the depth of the crater where the rock has to come out of. And that is an input in how much energy loss there is in tangential direction in the model. Since we started talking about these block forms, we have very simple block forms. We have the rectangular block. All three dimensions can be different. We have the ellipsoidal block. It's really then rounded. The spherical, of course, it's a nice football. We all are the same. Or disc-shaped rock, where the smallest dimension is smaller than a third of the two larger ones. And this determines, of course, with those dimensions and the shape, how much volume there is, the moment of inertia of that block, and, important, how it comes down the slope. And there, Rockyfor is quite pessimistic if we talk about the disc-shaped block, but also the others, it assumes that it will roll down over the smallest axis. So the roughness and the effect it has on the energy loss of the block is set in relation to the largest circumference of the block. And if you look at the impact against trees, since the block is on its smallest side, the probability of interacting with a tree is smaller than if you take a block that has 1 by 1 by 1 meter. So there's no sliding on its big side. This is a disadvantage. It assumes that this block, the wheel stays on its side and goes down until it has no more energy or velocity smaller than 0.1 meters per second, what we said in the beginning. So I just have to zoom into the chat again. Fall direction, another one that is always heavily discussed. We have here a rockfall close to Grenoble, which we see in the back here. Oh no, sorry, I have to close the sun stores again. We have an automatic setting, which is absolute horrendous. Sorry for that. I don't remember when was the year of the event. I think 2009 or something. 2,000 cubic meters coming down, most of the material fine-grained up here, the bigger blocks down here, and some individual elements roll down into this field. You can see it here. It's not at all steep. We're talking about 12 degrees, maybe 15 degrees, but still this 33 cubic meter block that we see on this picture was nicely rolling, jumping, rebounding, bouncing through that meadow. And there you see a nice linear, but not always. In the end, you see a sharp curve. And these are typical realistic fall directions. This is an example from Norway. I mean, there are many Norwegians online. They maybe know this case. I have these pictures from Ulrik Thomas, where you see quite a rectangular block. It's not a perfect cube, but because of its shape and its slow velocity, it really makes this interesting form, whereas another one just continues straight on. So, of course, you can do this deterministic and completely physical, which REMS is doing, and also quite nice. At that time, we tried to come up with a stochastic algorithm, and with that, we could reproduce our experiments quite well. I mean, this is in the forest, so we have two effects. You see in white, these are the trajectories of the blocks that we threw down that slope. Here's the avalanche track I was talking about in the beginning. So the change of direction of these blocks is due to impacts on the ground, but the extremer ones, like here, is because of an impact against a tree. This one, because this is tree-free, this area, this is just a result of the terrain, and this one as well. So we wanted to reproduce that, and we used a fall direction method. This slide is not so important. In the beginning, I had a GIS approach, simple fall direction, then multiple flow direction, and in the end, we calculate now a real 3D vector since 2003 already. And this is based on the following. In principle, and this is completely stochastic, in principle, the rock comes in this direction, fall direction before a rebound. Here is the rebound. And then the tendency of that rock is that it goes straight on. It has 50% probability of going straight on. Straight on means it has a deviation between 0 and 5 degrees. And then with decreasing probability, we have deviations from that trajectory. So there's not so much physics in the fall direction. And if there's a change of direction, and this I do with Monte Carlo simulation, I pull a random number. The number allows saying, yes, we will change direction. The number also says how much. So as I said, with 50% chance, there's a deviation between 0 and 5 degrees. Then it quickly goes down, I think, to 19% chance between 5 and 10. And here you have a 2% chance of having a deviation from 55 to 60 degrees, if I remember correctly. And if there's a deviation from your original fall direction, it will always be in the direction of the aspect of the slope in that cell where the rebound is. And this is how we calculate how the rock is going down the slope. So completely stochastic. If there are questions about this, just ask me or write it. Otherwise, I will continue. The digital elevation model, we come back to this later. The effect of the resolution is there in every rockfall model we use. Of course, this is logical. I mean, if we have our real landscape modeled by a terrain model where we have cells that represent 10 by 10 meters in reality, or 5 by 5, 2 by 2, or 1 by 1, we have more or less detail. And more or less detail means changes in the fall direction, changes in the slope, changes in the aspect. And there, I think that's the most important thing that we have to keep in mind if we start modeling rockfall. First of all, that we're using a model, and if it's very, very sophisticated or less sophisticated, they're both still models. I always like to say to my students, if you go to do a ski tour in a high mountain area, maybe those of you who live in Switzerland have full confidence in Meteor Schweiz. They will only look at one meteor site. I myself prefer to look at 4 or 5 of them. The French one, if I'm in the Mont Blanc area, the Swiss one, a European one, what is coming, what is the low and high pressure areas, and you make your own model of what you can expect the day you're going to make your ski tour. I say this because I see too many people just relying on one simulation with one rockfall model that provides the basis for their hazard mapping. And I think we should see the model as 2 things. One, that orients you hopefully in the right direction, how reality could look like. And 2, it allows you to ask questions if that what the model shows you is really the truth, and what could and how far it could deviate from the truth. So it helps you asking the right questions to come up with a proper answer. So it hopefully also surprises you sometimes what a model spits out, and then makes you as an expert start to realize, maybe I need a second or third model approach to come up with a proper answer. To remind us from that difference between reality and model, I just have here a picture that is along this road here, and this is the terrain as we see it in our detail, because this is already 2 meters. We can also show 1 meter. We'll do that later. There is some difference between what we see in reality and what we see in our model. I mean, there are different undergrounds here. There are like these protective boards along the roads, which will up to sometimes half a cubic meter in its deposit area will just stop the rocks, which will not happen in your model, etc., etc. So this is the input, and always realize what is not in my model. What does the model not see that I did see in reality? For example, our Vaujany, where we did the experiments in the forest, after 50 rocks, our slope looked like this. This is the same position in the digital terrain model. You're standing here on the forest road is here, and you look down, and this is what you see. In terms of morphology, this is quite okay. I mean, the steepness and the orientation of the slope is represented, but what is not at all there is all that material lying on the slope. For each rockfall model, being Rams, Rockyfor, or others, this is the hard terrain. And if the rock impacts that terrain, it will change the terrain during the impact. Not only because it's its penetration depth, but also because it creates a crater which is sometimes different shapes depending on the underground. So that is something that we need to take into account. So we can now think about elevation models or topographical DTMs, digital terrain models, that are very, very precise. And we do have them, of course, nowadays with 25 centimeters, 10 centimeters, 50 centimeters, where each and every bump is represented. But in reality, a big rock, like we take the Everland example, maybe you know that movie, I don't show it today, but in the paper of Noel, which I will cite later, you will see this 300 cubic meter block coming down and completely reshaping its own terrain. We have been in the fields, we're standing in the craters, they were 1.5 meter deep and 15 meters long. So this idea of the rock coming down, shaping its own terrain, has to be incorporated in the modeling. And if you have all blocks lying on the slope representing in your terrain model, these are just small trampolines where the block will just jump over, whereas in reality, it maybe could just crush them and completely change the terrain. So think about that. If you tend to use very high resolution models, start to combine the roughness you see in the terrain and the roughness you have represented in your parameters with what is already in the terrain model. So we come always to the end of that first part, general introduction. Before we go to the workflow, I realize I'm a bit too late. I was afraid for that. Since those experiments we did, lots of new ones have been done, luckily, and science progresses and gives us new insight, which is great. I would like to share with you a video of the WSL SLF experimentations in the area of shears in Graubünden, and I hope it starts because it shows again the enormous variation we can have in trajectory orientations. That was a disc-shaped rock. Now we have a more rectangular block. Because of a tree impact, it just almost has a deviation of 80 degrees from down there up to about 5 meters on that tree. And you see that what I told you before, because of the forest, we can have these extreme deviations from its fall direction. And this has to somehow be taken into account. So really nice videos showing the variation we can observe. These are just 3, but I have also several of them. Now this video is going to show us our experiments in France. There's a nice little story to it. It was a cameraman who came filming us, and we put him at that position where you see his camera now, because we said after 250 rocks in 3 years, throwing down the avalanche track, which was here, we said, you can put your camera there. You're completely safe. We know that. We never observed a rock there. Well, he had to run away because one of the rocks that we threw that day passed 1 meter in front of his camera, which he hasn't recorded that because it was focused on that area, so it's completely, how you said it, not sharp, that image. So it's just telling you, even if you know a site from your experimentations, you have seen like 500 rocks you threw down yourself, you think you know the site, and the 501st rock is then doing again something different than all the others and almost endangering this cameraman. As I said, all the rocks that we threw down up there were granite, almost granite, slightly gneissic granite rocks, very competent, about 0.84 cubic meters. And this is what you see 220 meters after releasing them from a forest road up there. So some are still 0.8 to 1 cubic meters. Some are stopping on that road. The most are jumping over like this. Some more rapid, some slow, some missing the road, some jumping up very high, up to 3 meters after the road. A lot of rotation after the rebound, of course, but an enormous variation of what remained of that rock and how they arrive later. So even if you release quite similar rocks up there, 220 meters, you have completely different behavior, different shapes and different volumes. And before we continue then, and the news is coming, I saw the forum, I also have a nice video from not so long ago, last autumn. This is in Vallorcine behind the Mont Blanc. This is a rock mass fall, but then you see the fragments coming down. Fantastic rebounds and long rebounds, long trajectories with long phases through the air. There's another block coming now. And again, here you see, of course, further up fragmentation of the blocks, eventually becoming then one fragment. Voila, we continue. In the end, you have rebound lengths of 150 to 200 meters in the air. So it's a really impressive and nice video showing with those steep topographies that we can really have impressive trajectories. The main steps, preparation. The best is if we, of course, have historical events, existing studies, but in some cases we do not have anything and we have nothing in the field deposited there. You're just in a virgin terrain. You can read that if after my presentation here, I will go through it, not all the details, but before we go into the terrain, it is fantastic to have a good field map. And nowadays with perhaps you can change color and size of the cursor. I'm not using it for the moment, but I can. Pointer. I'm here in the preparation. What I use a lot is hill-shaped maps, and on screen I start digitizing the polygons where I expect that terrain characteristics are similar. So meaning going actually to geomorphology, what was the genesis of that terrain unit? Is it a debris flow deposit? Is it alluvial material? Is it a transit area from a rockfall slope, which has been covered by vegetation since a long time? Is it a free and active talus slope, etc., etc.? So I start digitizing those units already in the office based on the slope map, a aerial photo, and the the hill-shaped map. This one B is a complicated one, as everyone knows, hopefully, especially those who are doing this for a longer time. The release locations. You have a relatively homogeneous rock slope. Excuse me. Can you? I'm sorry, my mouse is not reacting.
Invece ha detto che da noi non è così disturbante.
So, sorry, I have to mute those. There are, within a homogeneous cliff face, rock face, there are areas, of course, with different geological structures. And as you know, we have less and more active areas. So for doing a hazard map for a whole commune, and it's difficult to define that or to differentiate in there. It takes a lot of time, and it's also complicated to realize that. What is the different return period of, or the release probability from those areas that have different activity? But somehow you have to do it, and somehow you have to fix where they're coming from, what's the size and the shape of the rocks, and if possible, of course, how often is rock falling out of that. For those who didn't know that, we have a new tool. We're working on it still with a lot of field observations. It's called rockfall, which is especially for doing so to define the frequency of different release scenarios from a cliff. So rockfall, you will find that on the ecorisQ website. I don't have time to put the link. Maybe someone can. This is free for all, since it has been financed by public money in Switzerland. You don't have to be a member to use that tool. So rockfrag allows you a bit to define the temporal occurrence probability or the release probability. So you do your simulations, and there you have to start varying parameters. If you use REMS, Rockyfor, whatever, you cannot just, for one scenario, just simulate one block form with one given dimensions, because they're all going to show different results. If you throw a rock in Rockyfor3D of 1 meter by 0.9 meter by 1.7, you have a given volume, about 1.4 probably, 1.5. You can create another rock with a bit of other dimensions, and you will see a different runner. Thank you, Karin, for doing that. So think about that. Use different dimensions with the same volumes, or even use different volumes, slightly different volumes, to see what is the range that you can expect. So play around with parameters, and the same is true for the underground parameters, since think about Tramin in Südtirol, in Italia. There we had a rock mass fall and a few blocks destroying a part of a farm, and one block rolled next to another block which was lying there. And this happened in, if I remember correctly, in January. And the question is it extremely wet, your soil? Is it frozen since 2 weeks? All that will make that your rocks will make different rebounds on that slope. So it's not that we can represent all those different situations, but you have to choose one for your hazard assessment that you're going to use. So also play around with underground or soil types, and play a little bit around with the roughnesses, just to see how your model reacts. The plausibility check, of course, if possible, with your field observations. If there's nothing, it's getting difficult. Compare it with other modeling approaches, and play with your simulation until you have the feeling as an expert, well, this represents what is really happening, or what is relevant for the hazard at that given location. So fixation of the model results, removing outliers, defining the domain where it's valid, where you think that is valid, and then transforming that into intensity maps. And what I've seen when I was working for the highways, that there's a tendency, and I say this a bit for the younger generation without sounding as an old white man here, that there was a tendency of using the modeling results as the final results of the hazard assessment. And I think, this is my personal opinion, there should be always this step from the model, together what you've seen in the field, with the historical studies, with the existing protective measures and how they could react and how old they are, how many trees are dead, how many are still alive. All that is difficult to put in one single simulation, and all that is going to define in the end what is your answer when you make the hazard assessment. So the model is just one of the elements before you get to the intensity maps, and this is quite Swiss. I will come to that. So this I said before, maps prepared for the fieldwork, orthophoto, slope map, the hill shade with the first polygons before you go into the terrain, and then you can make them finer. Map to the terrain characteristics, of course, soil type, roughness, all the silent witnesses you find with the sizes, locations, all the protective measures. And of course, if possible, in what state are these? I mean, is it a completely new net of 7 meters high, 5,000 kilojoule capacity, or is there's an old wooden beam steel combination barrier that is 25 years old? Well, I think everyone gets that. It is important to try to bring it into your hazard assessment. What is now in the current version and in the older also the minimal data set you need? So you need a digital elevation model Preferable still for me, cell size 2 meters. It can go to 5 meters. It's a bit more general. Rocks will travel a bit farther in the new version. To avoid you have too much detail in your terrain, detail that is, and probably François Noël, he used another approach with his point cloud, but in Rockyfor, I think you're still representing reality most if you use a 2 meter, but I'm still testing that. I'll show you some examples later. You need all those rasters that I mentioned here in an ASCII raster format. It is a bit old-fashioned. We're making something that you can also read GeoTIFFs. The advantage of an ASCII raster format is that you can check what is in your data before you start modeling. You can open it in Notepad++, for example, which I recommend, or there are also others, but not the normal Notepad. It cannot deal with big data sets. Notepad++, you can see what data you have. You see your header, which is readable and clear, and you see the real data. Do I use points or commas, which we have often in France, and then the model cannot read it. So therefore, ASCII raster is really nice. A rock density raster, defining the rock density, but also defining the release cells. If it's 0, nothing is going to start there. If it's 2,700, it's 2,700 kilograms per cubic meter for calculating the mass of your block. You need 3 slope, surface, roughness rasters, and you need a slope surface type. And with that, you can start modeling. This comes back to what I showed you before. Of course, you have to, and this is in almost every, not in every, we're developing something which doesn't use this, but in 3D trajectory models, most of them, if you want to do it properly, you have to describe your different terrains you see in terms of underground hardness or elasticity, and not for all models, but for Rockyfor, you do the roughness, and you see the roughness here and here and here is different. So that is what you have to tell your model by making maps of that. How are we time-wise? 13:26. Okay. The roughness, read it in the manual. This is a short explanation. The roughness is what the rock encounters as a potential barrier. So of course you can have lying big rocks, like everyone knows those Taylor slopes where they're 2 by 1 by 0.7 meter rocks are lying on top of each other. This is the egg carton in French, or the egg box, you know that from the supermarket, that has to be told to the model how big is your egg box. What is the difficulty to overcome this roughness? And since the variation is enormous everywhere in the field, we fixed 3 classes, and we fixed a 70%, 20%, and 10% roughness that you encounter in your terrain unit. And these are the values you have to give to the model. If you have a nice grass golf green in the valley, it's all 0. Very easy. In the cliffs, in the starting zone, make it all 0. It doesn't make a lot of sense. In any case, there is so much energy that rock will continue and go down the slope. It starts to become important, especially important below the cliffs in the transit zone. There's where the roughness is extremely important. As soon as you enter the flatter areas, in many cases in the terrain, normally there's not so much roughness anymore. When I come to the valley floor, of course, also flatter areas with a lot of deposited blocks, then it's important. So if there is this roughness in the terrain, it's important to get it more or less right. And therefore we use these 3 classes, and that's seen as the rock sees it. So not from the valley to the cliff, because then you see a lot of roughness. From the cliff to the valley, looking down the slope, what does the rock encounter in terms of roughness? Determined in 3 different classes. Why? Well, during our experiments, and also this is again in these 5 years in France, we analyzed what is the tangential energy loss in an impact crater. I saw that someone, the unknown user, put indeed the pictures, if I recognize well, from Evolen. So you can look in the chat what the 300 cubic meter block. Now this is the rock going to the side, I think, looking at it. Oh, there's a typical impact crater, and you see what it creates. In that impact crater, the rock will encounter an obstacle, being it lying there already or because it penetrated so much in the ground. And this is what we call the mean obstacle height. That's the obstacle that the rock has to overcome out of the crater again, or just because it's an obstacle lying on the slope. And we found this nice relation that you see here. I agree, there are not hundreds of observations of it. It's what we could at that time, where we had good videos of how fast the rock was before and after the rebound impact, the impact on the ground, the rebound. And this relationship is built in Rockyfor3D with the idea to not to ask the user to give a tangential coefficient of restitution, this RT, but to give the model something that is observable in the terrain. How big is your rock? You define that by your dimensions, and then we take the radius of that rock, and the mean obstacle height is divided by that radius. So we have here two things that are real, that's observable, and it allows that you don't have to redefine your RT as soon as you're going to simulate bigger rocks. Because if you do so in traditional models, you had to change your RT depending on the size of the volume you were simulating. So that is a good point, I think, that we can fix, or the model calculates the tangential energy loss on the basis of what is lying there and the penetration depth and the size of the block. So some examples, you find this in the manual, so we go fast. These are the roughness values, and this is the soil type value. You see the example here from the field sheet, which you can see in the manual. The link to the manual, you find that in your PDF in the link to the course material. For the soil types, we haven't found a solution yet. Most models have that, just a description of the surface slope type, surface type, fine material, etc., etc. You can read it here. Oh, I see this is an old one. Excuse me, copy pasted that from a longer time ago. 7 is now the asphalt road. So don't look at that. Look at the manual, please. And behind the soil type, we have our N values, or the normal coefficient of restitution, or another way said, it's a combination of rock kinematics and elasticity of a soil. But you can read many articles on this. There are N values bigger than 1, depending on the algorithms you use. For Rockyfor, it's not important that you see those values. It's important that you use the right soil type. This is the last one, no, almost the last one. This is an example of this roughness of the soil. You see that here. This is this measured, so you have an idea. Parallel to the slope, about 25 centimeters. That is the largest roughness you see in that area where that rebound was. This is actually where a rock rebounded. You see some spots and specks on the rocks here. So there was a small penetration here, and everything was compressed a bit. And from that point, we measured what is the roughness in that area, and we also measured what is the velocity before and after. So coming back, you have these model input maps. You have the digital terrain model, the surface roughness and elasticity, your start cells and tree positions. And then if you come to hazard zoning, again, the modeling is one element of that. You have to combine everything before you make that step. But for the model output, I would say the reach probability is an important one. The energy line angles, which is an additional help. How realistic are my trajectories? If you have angles that are below 26, you can start asking questions. Is this realistic? But everything between 28 and 40, no problem. And of course, you need the energy. If you do it in a Swiss way, you make intensity maps where you're going to define in which area we have low, medium, or high energies. If you want to know more about that, I put the link in here. This is the geo portal of Canton Nidwalden, where you see for the 30, 100, 300, an extreme return period is 1,000, but I agree with you. It's difficult to fix that for rockfall scenarios. I think everyone is, but still it has to be done to compare it with avalanches and flooding. That's the idea. There you see their online intensity maps, what it looks like for rockfall in this case. Last year, and here I have to thank Christoph Schaller, who is also online here, we finally, after some critical remarks from François Noël and his co-authors, we said now is the time to dive into it again. It took us 8 days for both of us to improve the Rockyfor3D model and find some old errors that we knew existed since a long time. And so we finally came up with this version 6. I'm really happy we did it. And I hope you as well. Bringing new versions always brings discussions. It even goes so far that there's some members, for those who don't know it, but you can get Rockyfor3D today for free. But if you want to use it longer, you have to be a member of the association. The goal there is, and now 1 minute of publicity, the goal there is not to make money. We have a small budget. We have about 70,000 Swiss francs per year that we can spend. You can see this in our annual report. But for that, a lot of people are working on all the different tools that we have online for debris flow, bank erosion, name it, tree detection, also Rockyfor3D. And there are also some software people working with us, and this money that we get from the members, we can use it to develop new tools. And this money is then invested in such a way every year. So you're really supporting an association, and together we become better. That's the idea. I think it's still recording. Yes, we will see how we can make it available. Voila. So what I wanted to say, there are some members of ecorisQ that write me, please don't change anything. I like it the way it is right now. I got used to it, and I like to keep it this way. And this is always a bit of a problem. So for those people, we have the old versions still online. But for those who thought, and including me, that there were some pessimistic trajectories coming up with using Rockyfor, some pessimistic energy distributions, for those, I think the version 6 is better. Which not so good is that with the old version, we could, in most of the cases, simulate the surprises we saw in reality. Let's say the one in how many thousand surprise with a very low probability, we could simulate that. And one of those was the block that fell down on the Tesh golf course. No problem. We had not a high probability of a block arriving there where it did in reality, but we had some trajectories going until 5 meters before. This is not possible anymore with the version 6. We have to realize that. I tried everything to put the most pessimistic version. We could get the rocks up until the road on the dam, but not the last jump over the dam. I could just not reproduce it with the new version. So keep that in mind. Use also other tools to surprise yourself and to come up with the right answer. Sandra, have Noel tested the new version with their data? I have no idea. Let Francois answer that. Put in the chat, please. Okay, let's start. Version 6 versus 5.2. Well, here you go, Francois. Thanks to the analysis done by Francois. We realized, and I don't give the defense, and I don't give the explanation of why that happened. We used to have a very pessimistic approach for the rock-tree interaction. It used to be very much okay in my first MATLAB versions, but then at a long time ago, a mathematician worked on optimizing our code. And at that point, that person made a very rapid rock-tree interaction code, but unfortunately changed it in such a way that only the center of the block was interacting with the tree. So not the block as with its complete shape. So only if the center of the block hit the tree, there was a tree impact. Then with Christoph Schaller, we also found some other errors, not a big one, but every tree had an index based on the row and column. Well, there's not many trees standing on 2 by 2 meters, but it could be the case that if you have a thick one and a thin one in 2 by 2 meters, or they had both the same index, and only one of those random was taken into account. Now every tree in Rockyfor3D has a unique index, so every tree is taken into account. So this also, next to a real block tree interaction that we have now, you will see that there's a higher protective effect of forest in compared to the older version. Then an important one. Sorry, I have to change my pointer again. We corrected errors that in exceptional cases led to extremely high energies. We had, when you leave a cell in a DTM in a corner over the cardinal directions, cardinal means north, south, east, west. When you left the cell in such a direction and you came out of it, then the rock was moved in between two cell corners, and with that increasing velocity, and in the end having light velocities. So I never figured out where that error occurred, and I let it like this a long time, and I fixed the velocity limit to 70 meters per second, and then cut off the simulation, and that led to these energy sparks that you sometimes had in a single cell. So this is gone, and we don't have a max velocity anymore, luckily, because we found where the error was in those 5,000 lines of code, thanks to Christoph Schaller. Now we reintroduced the friction and scaling function. I had it already in the beginning when I started, because Rockyfor3D is very much based on Pfeiffer and Bowen, but I found it at a given time when I was in Semagref and checking the Rockyfor3D results with the experiments we had, with the old parameter settings and the old approach, how we modeled it, it was too optimistic. So Noel also in his paper put them back again with new parameters Pfeiffer and Bowen used. And with that, I think we have okay, but optimistic, realistic energies. So if in a few years we come to the conclusion that and we have better measurements of real energies, so for that we need a lot of experiments to validate the new algorithms we have, that would be great. Then we can maybe come up with parameters that that correspond perfectly to reality, but for now it's a bit difficult. Fourth point, and I haven't had an opportunity to discuss with Francois. I think he's here. Are you here, Francois? Noel?
Yes.
Yes. Oh there. Good. You wrote in your article, you found this extremely nice relationship, and I like that because Rockyfor is always based on progress of also others, not only our work, also when we began. And I thought the relationship was so nice that you found between the total deviation and the, let's say, the energy restitution. I thought this is a solution for those extreme deviations that we saw, but for my taste had too much energy restitution. So if a block changes enormously direction, or the total deviation is actually a resultant of the incoming and the outgoing direction, sorry, I'm losing my English. Direction vectors, and if there's a lot of change between incoming and outgoing in horizontal direction or also in vertical sense, then this figure published by Francois' article shows that if there's a big difference, there's also a lot of energy loss. And since in my model they are deconnected, the physics of the direction of the trajectory and the physics of the energy of the block, this relationship is a good solution for Rockyfor3D to reduce the energy restitution for the extreme deviations. I did not use the relationship that Francois published here. I took a pessimistic version. It only starts to work if you have deviations bigger than 55 degrees. So in this area, and there I more or less choose the upper line of these points, so not to be too optimistic. You can see the details in the manual. So this is also a big change in the new version. Another nice paper based on the experiments of the SLF is that finally there is a relationship between block form and maximum rotational energy, block form and block mass, shape and mass. And this is published by Kavietzel and al., a really nice paper in Nature. You can find it if you type rockfall Kavietzel Nature. And this relationship has been built in because the rotational velocity is a difficult one in the rockfall modeling. There are enormous rotations, especially with smaller blocks. The big ones, because of their inertia, they're turning a bit slower. And with this relationship, we can keep the rotational velocity within a realistic range. So this is also really nice. The next one is the error of blocks traversing a net in exceptional cases. I had many emails about that, and I had looked it up, and I knew where the error was, but we didn't have 1, 2, 3 solution, and we decided to do it with the whole overhaul of Rockyfor3D. So we did it. What could happen before, if your net was like this, very diagonal, so not east-west or north-south oriented in your DTM. And since we use raster data, because I'm not an IT expert, I'm just a geoscientist who learned programming, we are not working with the real lines. We rasterize your, as you know, probably your nets, we rasterize them, and a net of about 8 meters, if this is 2 by 2 meters here, is represented like this. The manual is online. The link is in your PDF, but you also find it if you go to the ecorisQ website. Maybe if someone of those participants has found the link, you can also share it. I don't have the time, unfortunately, right now. So if you had a diagonal net like this and the block came from this cell to this cell and passed precisely through the corner of the 2 cells, you move from one, very much, thank you, Niels, you move from one no net cell to another no net cell, and there's no effect of the net. So we said this is not acceptable. So what we do now is this round here. This is the block representation in a planar view. And then if we see there's an interaction between 50% of the block parameter with net cells, then the block is really in a net, and then the net will start to work. So with this, we don't have blocks going through the net where it should not be. Okay. If the net is working, that depends on your jump height. Of course, if the jump height of the block is higher than the net height, there's no effect of the net, as in reality. If the jump height is lower than the net, and that means really up to the level of the net, so if you say my net has 2 meters of height, and we assume that it's perpendicular to the slope, it's difficult to show in the movie, in the video, perpendicular to the slope. So we compare perpendicular to the slope height of the block with the perpendicular height of the net. So if you put in your raster that your net is 2 meters high, that is the effective height. So if you have a 2 meter 50 net, it's maybe better to put 2 meters in your simulation, or 2 meter 20 or whatever, depending on the block size. So if the block is in the net, lower than the net height, then the energy will be taken out of the block that the net can dissipate. We'll have a look at that later. And lastly, we included new options in the graphical user interface, like the rapid automatic simulation with low and medium roughness, a demand from Norway, if I remember well. We also added the cliff area weighted number of simulations. I'll explain that later. And also practical, if you come to realize you started a not so good simulation with the wrong settings, you can stop your simulation. That is also practical. So this is what it looks like. You have here your working directory, nothing changed. You have here your cliff area weighted, or your fixed number of simulations. So if it's 100 and it is fixed, then it is 100 from every start cell. If it's cliff area weighted, it depends on the slope of your start cell. From the steeper start cells, there will be a lot, much more than 100. If they're flatter, like 50 degrees, you will have less than 100. I'll show it later. Additional fall height. We created that a long time already ago for DTMs that are not so precise. Some people did regional analysis with 20 meter DTMs, and then you don't see your smaller cliffs. So you could lift your block from the terrain model and drop it, and with that generate some additional velocity as if the block would fall down a 5 meter cliff. So that you can do for this. You can also use it if you want to have more release velocity. So even if you have a good DTM, you can lift your block a bit and you give it a bit more push in the beginning. Variation of rock volume, that is really if you simulate 1 cubic meter and you put here 10%, you will vary between 0.9 and 1.1 cubic meters. And there you have your simulation type. So the user-defined input rasters, you are in control of what is simulated. There are two other options: automatic simulation, rapid automatic simulation. For that, you can only give a DTM. And then it will, if you define the rock density, it will calculate potential release areas, that is in relation to the cell size. And in general, for a 2 meter DTM, you will start simulating blocks from all cells that are steeper than 55 degrees, if I remember well, or 52. And if it's 1 meter, it's 55, something like that. And from all those cells, Rockyfor will generate trajectories with a low roughness option or medium roughness option. Those values have been fixed by us. You see them in the manual, so I have an idea what we're using. And there, based on the slope steepness, we will fix expert opinion, like we fixed some roughness values that might be realistic. But so don't use this as the truth. This is a first rough view of how rockfall could look like in your area. But of course, it's better to prepare your data yourself. The protective measures, you know, simulation with trees, without trees, using two options. We'll talk about that later with nets. You can define your block dimensions. It is then the same in every start area. You can define your release areas over the raster rock density, or you define a rock density value here for the rapid automatic simulation and your block form, and that's it. I think we'll keep it to that with the graphical user interface. So it's not a full GIS. For those who have never used it, I saw a question before in the forum about, are you going to change SagaGIS tool for some support and further development? Saga will stop soon. All right, Michael Mölk, yeah. Hello, Michael. We use a lot R Studio to prepare our input data. So that is also a option that will not stop soon. And the other one, people, and maybe we can share that a bit. We have it on the ecorisQ website. There are also tools for ArcGIS, automatic preparation. We can think about a QGIS plugin. That would be an idea. But we will share already the one we have in R. So just why do I say that? The graphical user interface uses the input data you prepared elsewhere. It will probably, I would never say never, but it's not our idea that we have a complete Rockyfor3D GIS where we start to draw your polygons here on the screen. Cliff area weighted release. We came to the conclusion in a risk project we did with the canton of Bern, and here my thanks go to the canton of Bern in doing that project in the pilot area of Adelboden, where the idea is that we do a full risk-based hazard mapping. So in science, we have been talking a lot about that since many years, meaning that for each release area, you're going to define your release probability. So yearly, monthly release of rocks with power laws, and then simulate the runout with and without forest, with and without nets. And then at each cell, you can calculate, of course, a probability of occurrence when you multiply the release probability with the reach probability. And in that project, we came to the conclusion we have to fix those errors of Rockyfor3D and give it a proper update. And we also came to this point that you cannot use anymore a number of simulations. You have to somehow account for the fact that a steep start cell, this line here, so we have start cells of this, let's say 2 meters here, and this one as well, and this one as well. And one start cell is 45 degrees, the next one is 76 degrees, and then the last one here is 83 degrees. And it's logical, of course, because of the steepness that we have a different slope surface, rock slope surface, and the bigger your slope surface is, the more production you could have. I mean, it can rightly be that this is a very active area, and down here, there's nothing compared to that above. In that case, don't use this, but for a large area, for an area of several thousand square kilometers, you cannot define this. And the first approach is then to say, okay, steeper areas produce more than the less steep areas. And that's why we use the cliff area weighted number of simulations. So you still define the number of simulations in the graphical user interface. You say 100. Based on that number of simulations, and the slope, we calculate the actual number of simulations from that cell. So if it's 83 degrees steep, you will get 403 rocks coming out of this cell. 206 from a slope of 76 degrees, and if it's 45, it will go down to 71. If you have a 60-degree slope, then you have exactly the 100. So you have a differentiated number of simulations depending on the steepness. That's what the cliff area weighted number of simulations is all about. I hope it's clear like that. It's also written in the manual. You can read it back if you want. So now, time 15:10. Yes, we have to progress, Luke, faster. I will take you to an area which I've been myself twice, but I haven't mapped it on the terrain. That was done by the team of Marco Stoffel long time ago. And I thought, let's go back to that area to use it as an example for today. It was a random one. Here we are in Flash, the village of Flash, which has the Pinot Noir grapes for the wine here. We're in the border between Liechtenstein in the background, almost Austria and Switzerland. So we're at that interaction. That's a 3 country point, and so here we in Flesch. The geologists among us directly see this is probably some sedimentary rocks. That's true. We're in the Helveticum here, and we're in a marl limestone area. And the cliff we're going to look at now in the example is this one up here. This is a nice tourist, how do you say that? A tourist card of, I think already 40 years ago, but it was a nice picture to use today. Okay, this is the area, this is the village. There has been a rock mass fall from this area here that came until there. From that, about 4 or 5 years ago, there was a debris flow destroying more forest. That is the lower part, but the actual deposit from that rock mass fall, not very big. It was only several hundreds of cubic meters that was lying here. That 2.9 cubic meter block came from there, went into the forest and stopped here. Those other 1.1, 0.6 and 0.6 down here are fresher blocks that came down after that rock mass fall. So this is a bit of the base that I used to look at different simulations for you today. The village is here. You see the vineyard, you see the forest, it's a mixed forest, and you see the cliff area, this one to the side, and that bigger area here. You see that better in the slope area. For those who start with rockfall modeling, as I said in the beginning, I use my hillshade, which is nicely showing the morphology of the terrain, and I use a lot the slope map to see where are my potential starting areas, and that gives an excellent basis to make a first differentiation of source polygons. So you see the slopes, the village is down here. You see the terraces with the vineyard here between 10 and 20 degrees. Here already much steeper, 20 to 30, and then we come into this transit area here where we are between the 30 and 40 degrees. So with the new version, and I just took a small starting area, which is a bit above the rock mass fall from 2013, which was here. Just to have a small area, so it's not a complete mix of many trajectories. This we're going to use to compare the old version with the new version. So this is a simulation of 3 cubic meters. 3 cubic meters is the block that's lying here. This block is a disc-shaped block. It's really flat. It's 2.5 meters by 1.7 by 0.6, so really thin plate. And this makes, as I said before, if we simulate that in Rocky4, it's like my iPhone going down the slope, or rather my book here. You don't see it. And it's falling like this down the slope. So it will always, it being a standing upright wheel, which is of course a pessimistic view. The only thing is, if you have those blocks, and we also have films of that, they can do that, and they will, if they don't hit a tree and they once get up and there's no huge impact, like we see in Evolen. That's a good example of a wheel going down very far the slope, and in the last counter slope after traversing a forest, have a look at the movie, it then falls on its side and then it fragments. And then it stops rather quickly because it's sliding over the slope. Well, this effect, we don't have it in Rockyfor3D, so we have a pessimistic view of these disc-shaped blocks. But nevertheless, I plotted here the reach probability. I will come to that later. And the number of blocks stopped. So you see the majority stops here and here, but all along the slopes, we have block stopping, even some that will not leave the starting area or stop in the upper part. So do we reproduce that event? Yes, we reproduce that event. We say, well, that's possible. There are some blocks stopped here and also a lot of them here, but many of them also continue further because of this pessimistic approach that we have and went down all the slope. Are both possible? I don't know. I cannot prove it to you. Might be. Difficult to say if all the disc-shaped blocks will, after tree impact, glide on their sides and stop. Difficult to say if 70% indeed goes until here or until here, until here. So this you don't know, and difficult to validate. So this is the 3 cubic example. Now there's 0.6 cubic meter. One fresh one we observed here and the other here on a forest road. This is the reach probability we get if we use the settings of the Stoffel team from the University of Bern that time, so it's a longer time ago. Then this is what we observe for 0.6 cubic meter with forest, and that forest is the forest that we use right after the rock mass fall event. So the upper part here was destroyed, and down there we have trees all over the place. Now, of course, this 0.6 block, as so often in the terrain, it's a bit difficult to say, does it come from here? Or does it come from here? Or does it come from here? So that's why we also simulate an option with all the potential source areas that might end up here. And when doing that, 0.6 cubic meters with the new version, we see that we're right in the middle of a high probability area for 0.6 cubic meters. Okay, again, with the trees, all the sources. So what happens if we take the if we take the trees away, so no trees at all, we see a complete change of this to this. So there's nothing on the slope, only the roughness that has been mapped by that team at that time, and this is the image. I show you this because we have to realize, as I said in the beginning, in the old version of Rockyfor3D, the forest had an extremely pessimistic, was integrated extremely pessimistically. Only the center of the block was taken into account when hitting a tree. So I think this is the best one to compare with the old Rockyfor3D, but there we go with trees. This is the change from this to this. So 0.6 cubic meters, yes, ending up in the valley, but with a low probability until here, it's probably, maybe until here is still probable from that area. And if you now look at the old version, much more pessimistic. Unrealistic completely, I don't know. We have to ask the local vineyard owners if they had 0.6 meter blocks in their vineyards. They're not entering the village, which corresponds to reality, but we see a huge difference, and especially now if we, I'm sorry, this is the new version with forest, and this is the old version, excuse me, back. This is the new version without trees, and this is the old version rolling into the village. So extremely pessimistic, but with a low probability. And if you then take all the trees away, then you have this quite pessimistic view. So that's also what we knew, as I said, we knew that it was pessimistic, and now we have a completely different results with the new version. Interesting also is the effect of the cell size. Again, this is 0.6 cubic meters with the new rockfall version. This is with the trees, and this is if you start simulating with 50 centimeters. This is if you do it with 1 meter, and this is if you do it with 2 meters. So you see that if you take a larger resolution, I didn't simulate 5 meters, but I expect that we have an even longer run out. I'm very much a fan of the 2 meters because I think, in my opinion, for Rockyfor3D is a good compromise between a detailed terrain without taking into account every single block that is lying on a slope, which can be moved by a block that is falling down. So what we really want in Rockyfor is what is the tendency as detailed as possible of the terrain, what is the orientation of the terrain and how steep is it, without every single little detail of that, the thing that is lying on the slope, because everything that's in the terrain model is fixed. It cannot be, how to say it, it determines if the block jumps up or if the block is deviate from something. So if you have a 10 cubic meter block and there's a 1 cubic meter block lying on the slope, or even 2, the 10 cubic meter will crush and remove maybe that 2 cubic meter block. If it's in the terrain model with 50 centimeters, it is there. It is fixed. This is just an obstacle. So with Rockyfor3D, the philosophy behind the model is to have a 2 meter resolution, because I think it's extremely difficult to pretend that we can model a falling block and it's 1 meter precise. So there also, I think the 2 meter is good. It gives a detailed enough representation of the terrain, and everything that's mobile and an obstacle to the blocks that are falling, you have to define by the parameters. That is the philosophy. So once more, you see it also in your slides, the 50 centimeters, the 1 meter looks very nice. If it is true, that's the question. 2 looks already less detailed, but it gives still a good enough representation for me what a rockfall hazard look like. But I leave that up to you, because as in every model, being it RAMs or whatever, you have to somehow fix your parameters and play around with them. Not that it fits your the image you would like to have, but it fits the image you tend to have as an expert there. And of course, best if you can have a foundation based on historical events, other studies, and silent witnesses on the slope. This one is for you. The parameter sensitivity on Rockyfor3D. It doesn't make sense to read it. It's just loss of time. Read it in your own time. Where is what important? Roughness and slope type. The summary here is, if you have a lot of roughness, you're probably in the transit area, you're probably in soil types 4 or 5 or 3. There, the roughness is extremely important. If you're in soil types 2 or 1, you're in the valley floor, you don't have roughness. So in 1, 2, and 3, it's the soil type that is really important. In 4 and 5, it's the roughness that is really important. And those 2 parameters are the ones you have to tune. Roughness, you can see it in the terrain, so I would not change it. And if you're not happy with the results, then I would either start changing your soil type, because as I said before, your soil type, if the soil is frozen or extremely wet, all that is not in there. And if you compare a historical event with a simulation, you might take into account it was extremely dry, extremely wet, it was snow, it was frozen, whatever. So the soil type is the factor you should tune first. Of course, the size of the blocks always has a medium to large influence compared to the other 2 parameters, particularly on slopes less steep than 20 meters, because then the penetration becomes also very important. Read that for yourself. That is just the input for today. Reach probability. Many years ago, we were thinking a lot of what is your basis to come up with fixing a line, saying that is a realistic run out for my simulation. There I would put the line based on what I saw in the field, what I simulated based on other studies. And we used to work a lot with the number of passengers, but the number of passengers is a relative thing. If you have a huge source area, you have lots of passengers. If you have a small release area in the same domain, you have not so many number of passengers. How to compare those 2? So we started weighting with the amount of rocks that could that are produced by a source area, small or large, and could end up in a given position. So we said the number of passengers have to be normalized with the number of simulations and the number of source areas feeding a given cell in the runout zone. So that's what we started doing, and we called that then the reach probability. The calculation, you see it in the manual, the number of passengers times 100 to come up with percentage. You can also leave the 100 away, it doesn't matter. 100% divided by the number of simulations per source cell and the feeding number of sources. Okay, so to visualize that, here you see for each cell how many source cells were feeding a given cell in the area below. So, of course, if one trajectory went through, of course, there can only be one source cell, that's clear. But if you have 1,000 blocks coming through here, you can have maybe 200 cells that feeding this location. And now, if you do the calculation of the reach probability, you suddenly move from a spaghetti image to something more readable, saying, okay, we have zones with different reach probabilities. Here we simulated 1 cubic meter, and you see also the events that have been mapped as such. These are the open circles. So some are not reached and some are very well reached. And with that reach probability, you can start drawing a line. Do I use every single spaghetti line, or is there a value that I use as a basis saying, well, that is a realistic runout zone? So this is the reach probability to show you how this changes. I again used simulations of 0.6 cubic meters from that area, and I do just one simulation. If you do one simulation, you have for every trajectory coming out one of the source cells, there's one simulation, every value is 100%. So you cannot really use that. If you do then 10 simulations, you have values between 10, 20, 30, 50, 50, 60, etc., 100% values. If you again go to 20 simulations per source cell, you will differentiate between 5 percentage classes, just because of the calculation, the way it's done. So you need at least 100 to start to differentiate between 1, 2, etc. percent. What was also interesting is when is your distribution of reach probability stable? When do your results convert, as we say in scientific language? If you have a probabilistic calculation, you change something every time. At a certain point, you reach a number of simulations that the distribution of your probabilities, in this case, reach probabilities, but the same thing for energies, the distribution is not changing. And that's the point we're looking for. So I give you the example of 500 and 1,000 simulations. So you see with increasing number of simulations, the extremes increase, they go farther, the area becomes larger, but the probabilities of those areas which are higher than you see it here, the values 1% are not changing anymore. I go back. So still between 100 and 500 and 1,000, you see some slight changes in the reach probabilities down here. But if you do really a sufficient number of simulations, 500 and 1,000, it's not really changing again. So do sufficient simulations to have proper distributions that allow you to make a decision, and not 10 per source cell, because yeah, that is not a stabilized distribution. Are there questions on this reach probability? If not, I'll continue. If you do, also later. Yes, François, please.
Yes, sorry for the feedback loop with the speaker before. So now I didn't mute the TV while I'm speaking.
Okay, it was you. No
very
problem.
nicely
maybe you can put on your camera,
probability
François,
on how it's normalized per feeding source cell reaching a given area. With the newly introduced normalization per source area,
Yeah.
is there a correction that is made here for
Yes.
the contribution of the source feeding cells,
Yes.
but based on their surface area as well?
Yes. Yes. Good question. So we're going to look not only at the number of source cells, but also how many blocks, given their cliff area weighted number of blocks they simulate, how many could end up down there. So it's also weighted for the area in the reach probability. Thank you for that question. Command line version, there is a CMD version of Rockyfor3D, and that allows you to batch a lot of different simulations. That's to separate your starting areas and to let the whole thing calculate overnight. Here's the link to the manual for those looking in the PDF. There's the description, also how this works. In the end, we can, with the remaining questions, we have 45 minutes and different aspects you can ask me. There you can do some tests yourself with this batching. In the file you could download, there is an example batch file. A batch file, for those who don't know it, yeah, I'm also looking at the forum. I see your comment. Thank you. It's noted. The only thing we need is time and a bit less money, but time is maybe the most important one. We'll do our best. A QGIS plugin. Excuse me, I need another coughing thing. A batch file is nothing else than a list of commands executed by your computer. And a batch file, and now I'm sorry for the Mac users, we're now looking at a Windows solution. The same exists surely for Mac, but I don't know because I'm not a Mac user. And it's really a text file that you give the extension BAT, batch. And in the text file, there's a list of good old Windows DOS commands. The older ones in the group still remember that, how we were working on MS-DOS computers and giving one after the other command, which is still the case if you're programming. What you're going to do in the batch file is to orient your computer to where you find the Rockyfor3D command X file. And so you have to find the path on your computer where this is stored. And the best thing to do so is when you start Rockyfor3D in your Windows Start menu, you look at the properties, and there you find to which file your shortcut is taking you. And in that directory is the command line version. So first, change directory, CD, take it there. Here you can put as many remarks as you want. This is not taking into account. It's commented out as another programming languages. Echo is something spit out to your screen. So if you do echo and what comes behind it, you will see that. And then you call for Rockyfor3D command line version. Where are my input data? That's the -p, the path, -p space, and this is where your data is. -s, number of simulations 100, -t, which tree option, 0, no trees, 1, a tree file, 2, forest rasters, and then the 3 dimensions of your block, -1, -2, -3, and this is a block of 0.2 cubic meters. -e, block shape, -e is block shape rectangular. Then you want to simulate without forest. Then you want to simulate all source areas. So you have a different rock density raster. Here you have a subset. And in your rasters, your rock density raster, which is in your directory here, you can define which areas you're going to simulate. And you put them all, you copy paste that and you adapt it, and then you do your your 100,000 simulations during the night. That's the idea with batching. Saves a lot of time. Preparation is all, and once it runs, and you can test it if your whole thing runs through by do -S1, just one simulation per case. If that thing runs through, then you do your 100 or 200 or 500 simulations during the night. All right, so this is an efficient way of working. Wanted to show you that. To understand this command, we have some help. You see that one here. Command example, and it is explained in text what it does. But as soon as you read the manual, I think with the examples, everyone here present manages that. Nevertheless, are there questions about this? So in the end, in Explorer, you just double click your batch file. That's all you do. And then you will see a black screen opening, and the echo will show you where you are. You can also write echo simulation case 1, simulation case 2, whatever you want. And then you can follow how far your computer is. Let's continue with accounting for protective measures in Rockyfor3D. For some, there are some old slides, but they're still good to explain it. And let's get deep into the details. What are the traps here? Tree impact. How does this work? Well, we have this trajectory of the center of the block. This is our block. So at every time when the block progresses, we can check, is there the interaction with a tree surrounding me? And when this is the case, so when this block is there, of course we have an impact. Then we have two types of trees for the general user. But there's some buts. You can do more, but I'm not sure I ever wrote that in the manual. It was a bit of our scientific version. You can, in the tree file, in the fourth column, you can give every tree a tree factor. 0 means it dissipates no energy. Tree factor of 1.3, you're reproducing a broad-leaved tree. 1.1, you're reproducing a Acer pseudoplatanus, or an Ahorn auf Deutsch, un érable en français. If you use a value of 1, you're in general close to the white firs and spruce trees. But if you want to, for example, say this tree has hard rot or something, you could say it dissipates 20% of its normal energy. So this tree of 20% or 40% of my forest has mortality, but are still standing. So I give them values like 10% or 20%. Okay, so this is possible. But in the basic version, if you define with the coniferous percent, and coniferous percent is a raster that for each cell tells the model 20% of the trees are coniferous trees, 80% are broad-leaved trees. In that case, at each impact in a cell, it's stochastic again if the tree is coniferous or broadleafed, because at each impact you pull a number between 0 and 100, and if you said 20% is coniferous, well, if the number is between 0 and 20, you will have a coniferous tree impacted. If the number is between 20 and 100, you will have a broadleafed tree impacted. What happens then at this impact point? Depending on the diameter of the tree, and that is given by your tree file, and then the stochastic decision, is this a broadleaf or a coniferous tree? Of course, if you have 100% coniferous, you have always a coniferous. I think that's logical. You will calculate, or the model will calculate, what is the maximum amount of energy that can be dissipated by this tree. So it's a dark green one, it's a coniferous, it's a really thick one. So let's say this is 60 centimeters, whatever. We end up around here. So 430 kilojoules is the maximum capacity of that healthy coniferous tree during an impact at the base of the tree, in the center of the tree, under an angle that is between 20 and 60 degrees. But if that is different, so if the impact height is 5 meters and not at the base of the tree can only dissipate 40% of that. There's less mass at that point. So it reduces quickly if you move up the tree, right? According to this function, the model describes how the dissipation of energy differs with the impact height. Then the eccentricity of the impact, also an important factor. It has now a strange shape because I used the latest publications that exist on eccentricity on trees, and I took the most pessimistic version. We used to have a sigmoid function that goes up here. All newest functions have this form. So I decided to take the pessimistic one of both, and that is this. So if you're 60% pessimistic, then it shoots enormously or drops enormously. So the height, the eccentricity, and the angle, this one comes from our research project Rockfall that we had with SLF and the UBC in Barcelona. And it doesn't matter. Oh God, I forgot it. Yeah, INRA, I think. Doesn't matter. And SLF found out with their test that there was also probably how the fibers are growing in the tree on a mountain slope, that there is an effect of the impact angle of the block on the tree. But this I just took over from their publication, Martin Johnson in 2007. So I never changed this one. I just left it as it is. So these are the 4 functions that determine then at every intersection of a block and a tree how much energy is dissipated. So you can do 2 things. You can make a tree file which has the position X, the position Y of the tree, and the DBH, and you need a raster with the forest type or the mixture, as we call it. So which percentage of trees in that cell is coniferous? That is what we have to write down in a raster called conif%.ascii. Otherwise, the model cannot know how many trees are coniferous. The other option is 4 rasters. I'll show you that later. The tree file is most easily created if you can detect trees. I'm not saying that you're completely representing your forest here. Absolutely not. If you do tree detection, there is one of the tools on the ecorisQ website, and it's still a quite performing tool, but in some studies we coupled that tool called FINT, detection of local maxima. We coupled that with machine learning based filtering of input data, and then you get much better results. But there's a publication on that of Christoph Schaller, but I think I can understand for everyone that is a bit difficult to use machine learning based tree detection. So FINT gives you a first approach. This technique is quite simple. You have a digital surface model with the trees and the houses. You have a digital elevation model, which is the last return of the laser scanning, which in most cases reflects the Earth surface, except in cases where you have a very dense foliage, leaf cover of your forest, and then it's difficult for the laser scanner pulses to go through that canopy and touch the Earth's surface. But in many cases, you still have a good representation of the terrain. So, and if you subtract the terrain from the surface, you are creating the Netherlands. The Alps become completely flat, and the only thing you see is open terrain, trees, and houses. As I said, you're in the polder landscape of the Netherlands, but in the polder landscape of the Netherlands, it's easy detecting trees. So then with that digital canopy model or normalized crown model or what you name it, there are many names for that, you're going to look for the local summits, and then you have the individual co-dominant trees. That's a typical forestry term. That means the understory, and each tree that has a crown below another one cannot be detected because you're detecting in the canopy layer. So you're detecting the dominant structure of a forest. You're detecting, is there a tree, is there no trees? But the hidden trees, you're missing them. So by doing so, you're creating a pessimistic view of the forest, which is in fact not that bad. We did do quite some research with our students on the effect of this, and I don't have clear answers already, because it means to see how good you're representing the efficacy or the effect of a forest, you also need to know exactly in what state every tree is. Is it rot in the inside? Is it dying? Is it wood? Characteristics are changing, and you don't see that always in the external externity of the tree. So you might, for all the trees detected, you might assume that they're completely healthy and they can dissipate 100% of that energy that we're giving to it with our functions. But this is a optimistic vision of the forest. So we have a pessimistic vision of the forest because we're detecting only the dominant trees, the big ones. We have a optimistic vision by assuming that they're all healthy. Are we too optimistic or too pessimistic? I still, after all these years, with all those studies, cannot tell you. Depends, of course, a bit of the mortality in your forest, and depends on how many layers you have in your forest stand structure. So there's no general answer to this. An example in Austria, this is a digital surface model. This is the digital terrain model. This is then the Netherlands with the rockfall dams here. And then you detect the summits we can find. Some of them you miss because they don't have a clear summit. That is not a perfect tool, that's clear. And we also define a minimum height of trees, so below 5 meters. Here we didn't take it into account as a tree. Then what you need, as soon as you have the trees detected, but the tool Fint can also do that, you have to give him a algorithm, and best is you can give it an algorithm that is provided by the Forest Service, and they do inventories and they have these relationships. Some of them include also altitude, because of course DBH and altitude is very often related. You can put a lot of variables in there because the forest site is important. It's a good site for the growing characteristics or not, but simple ones just make a link between the tree height and the DBH. And if you detect the trees, you have the tree height, and then you link a DBH to that with a random factor in it, because not every tree of 25 meters has 27.4 centimeters of diameter. There's a lot of variation in there, but I leave you to that. I don't have today, it's not the goal to go deep into fixing the trees. So with that, I hope to have answered a bit of the questions that we have concerning forest, vitality, mortality, detection of trees, and then there are many things to be investigated still. A quick focus on the other option. If you don't have LiDAR data, not every country has this luxury, of course, that we have in the Alps, and also in Norway, of course, is to use good old orthophotos, and where you start digitizing in your GIS your forest stands, the different stands you have. And for each stand, you have to give some attributes on number of trees, the mean DBH, the standard deviation of the DBHs in there, and of course, again, the percentage of trees that are coniferous. With the Saga scripts, and we also do that then in our future Python script, you can convert those in rasters, and these will be read and then converted into a tree file. So this is interesting. This is also interesting for our scientific studies, we sometimes do tree detection from LiDAR. We combine it with forest inventory plots. We see which trees we are missing, and we generate the understory layers in this way. And then we combine the two tree files, and then we have a realistic forest, except for the mortality, because that remains problematic. I have one eye on the chat. I have to read it later. Yeah, I don't have that master thesis, Sandra, here, but they must exist. They must exist. We don't have it, as far as I know, in our division. The next point are the questions about trees and how to integrate the forest. But there's one thing I didn't put in the PowerPoint presentation. There's always the big question of what do we do with the lying stems? If you look on the ecorisQ website in the old news, you go into the news section, you will find a publication that we have co-written and also co-financed on, it's in English, even in Italiano, German and French, on how to combat natural hazard with wood. And there it talks about, my God, my English, Wildbäche, torrents, avalanche control, but also a bit about rockfall. And of course, one question is decomposition of wood, and wood that has been treated with chemicals or not. The thing is, if we put logs on the slope to create additional roughness to stop falling rocks, fairly efficient, as shown by the SLF experiment, but also the experience that Fred Berger did in 2009 and 2010, where they used the Vaujany site, where we threw those hundreds of rocks, and where we then cut some trees and put them diagonally on the slope, only 6 of them, where we had in the forest 30% that went through the test forest up to the forest road and stopped a bit further. With the logs diagonally cut, all rocks stopped within that forest. And also Adrian Ringenbach at the SLF then, now at the ETH, he did his thesis on that. And they also imported some logs in the test slope in shears that I showed you before. Also there they could show that there is a big efficacy of diagonally cut trees and leave them on the slope. The question is durability. How long is this effective? Well, the data that exists, there are some theses on that, shows that broadleaf trees, they are efficient during maximum 5 to 7 years, and then they fall apart. So a beech tree, even if it's thick, after 7 years, it is really decomposing fast. With the coniferous trees, it can last up to 15, maybe even 20 years, but then you're extending it along, and it depends also a lot on what is the site like. Is it like a tailor slope, or is there a lot of soil? Is it partially in the air or lying on the ground? Is it north or south oriented? A lot of sun or not? So these are all factors. But meaning coniferous trees, if you do a management intervention in a forest, it gives you 10 years of, you're 10 years ahead. Sorry, it's not what I want to say. If you have a gap in your forest and you're waiting for the regeneration, so the young trees to grow up, you can mitigate that situation during 10 to 15 years. So there, it's helpful. It's also helpful for the young trees growing up because the lying logs are protecting against snow gliding those younger trees that are growing. Okay, but now, if you really want to integrate that in Rockyfor3D, there's not a really good solution for it. You can use small nets, but then you have very thick trees, like 2 by 2 meters thick. That's not really fantastic. We are using roughness a lot in our research to put it in as a roughness. But you will also see that if you have tree logs, except if you put them everywhere, that the area covered by lying trees is not so much. I mean, it's this long, thin match. If you compare to matches to light your candle, lying somewhere on your big slope. So in the roughness, it will often not go further than 10 or 20% increase of roughness. So that is one way, but it's not the most satisfactory one, but I don't have another solution for that. So this was a point I wanted to add to the whole tree story. Yeah, there's somebody shared the link of the study of Adrian. Okay, then an important one, working with net. The nets are also calculation screens, and it's actually the best thing you can use if you're interested in your energy distributions, if you're planning mitigation measures. Because putting a line somewhere, as you all know, it has been done since the 80s in our 2D rockfall models. You put a, what was it called then? Yeah, an analysis screen at that time. On that line, Rockyfor3D will collect all the information of all the blocks passing over that line. And so the best way to do that is create nets. And if you're interested in a situation where there is no real net, you make one raster with the net numbers. So it's again, and this has to be part of our future QGIS plugin as well. You digitize them as lines in your GIS. And every line will get an attribute, a number, a height, and an energy. So if you want to calculate with real nets, of course, you give the effective net height, as I said before. The top of a net is always hanging a bit. So even if you have supporting structure that is 3 meters high, your net in the middle is a bit lower. The other thing is it might not be that effective if your block hits the upper part where the cable is. So you might think about, and there is also information in norms, that Austrian norm. Michael knows a lot about that, what you could do to account for certainty, increase the certainty of your mitigation measure. You give the effective height of your net and you give the energy capacity of your net, and then it will be included in the simulations. If you put 0 or something, doesn't matter, you will always create, when you calculate with nets, you will always, sorry, I was looking at the chat again. You will always create a output text file, which gives you all the information on the line of the net. So here I did a simulation with nets, which you can do as well. You just use the input data that I put in the file you downloaded. There are many ASCII files. You need all of them if you want to calculate with forest and with net. There's also the tree file in there. And if you use 0.6 cubic meters, you will see something like this. I put a small net just to see the effect, that there is also something going through or over in this case. So this net here is 1.50 meters high and has a 500 kilojoule effect or capacity. Once more, if I made it 2.5 meters high, everything would have stopped. What you see with the jump, with the energy, as I said, it's no problem. This is the energy map, up to 300 kilojoules, so all stop in the net. But in the jump heights, you see that some are 2 meters high, flying over this small net, and that's why they continue further down. So if you have such a net, you create, or Rockyfor creates, a calculation screen text file with the date and the time your simulation was finished. So if you do this several times with the same blocks, you will have it all stored. And there you see all the information per net. So if you have very long nets, you have no idea where this is. So if you're really interested statistically how this varies, from here to here to here, you make one net section, not 1, the second 2, 3, 4, 5, 6, 7, how many you want. Because if you don't, as I did it here, this is all net 1, and I could put net 2 here, 3, 4, 5, whatever. We have simulations where we have like 600 nets. After, behind each house, we can make a net to see how many blocks are coming with which intensity and with which probability. So here is every block that entered that line or crossed that line. The velocity of the block, the energy of that block, the vertical passing height, the rotational velocity, the impact angle. Downwards from the horizontal is minus, upwards is plus. So most there are going down with more or less parallel to the slope, not all of them. And you see the normal passing height. So perpendicular to the slope. And up there, you will see for each net that you defined, you see the summary statistics. So how many blocks came in? 704. The 50 percentile of the energy, the 90, 95, 98. Maybe you should add the 99. I don't remember. In the Austrian norm, I think it's also 99. Well, the passing heights percentiles. So for those who are not familiar with those terms, a 95 percentile number tells you that 5% of the blocks have an energy that is higher than 167.5 kilojoules. Only 2% of the blocks go above the 185 kilojoule. Voila, those summary statistics are of course nice because then you can really think about planning or dimensioning a protective measure. As I said, if you put 0 height, 0 capacity, you will have the same file here. All the blocks that cross the line are registered. So that's also a good way to do risk analysis for given houses or roads or whatever. This gives you the information, or most of the information you need. 99, all right. I have to put it in my book. Good. Rockfall Dam. It's good that Michael Mölk is here. He knows a lot about that. And I answered the question, would it make sense to represent the tree logs on the ground in the dam by modifying it manually? Well, let's use this example of the dams here to answer that question as well. So here I did so. I integrated a dam, a rockfall dam, in the DTM. I used a very, very simple approach. I digitized the line. I gave that line a height. I think in this case, 10 meters or 8 meters. I don't remember. It's a long time ago. And I added that height to the DTM. So you rasterize the line. Everywhere it's 0, and in that line here it's 8 meters, 10 meters. You add that line to the DTM, and there you have your dam. So concerning the trees, but also for the dam, there are several things. If you put random trees on the slope, they are mobile, and the effect that they can move is diminishing their effect. And of course, if you put them in the DTM, but also in the roughness, it's there. It's not mobile. It's fixed. This biggest disadvantage I see is that if you work with 1 by 1, but also even more with 2 by 2 meter cells, you have enormous thick trees. You know, even if you say a tree has 40 centimeter diameter, so you raise your DTM, and they're mostly lying. A few of them cross. So I think you get a very strange DTM. I'm not sure what the model is going to do with that. So I would not represent the logs in the DEM. It's creating small trampolines which can happen with trees as well. But I don't think you get the best results there. Right. There are many questions coming now. Is there a reason why the confidence interval values are no longer displayed? Yes. I was never happy with that because the 90... Wait, no. Okay, keep that question for later, all right? When we come to the output. Why is the dam has a sawtooth shape? That's because the dam is not precisely north, south, or east, west. So it's a line that is a bit, where's my camera? A bit diagonal on the dam. Voila, that is why you see that. So this works well. You can represent your dam and the efficacy of it. What doesn't work is this is the terrain and it's unmovable. So a dam, as Michael knows, it can be, especially if you hit the crown, it can be completely devastated. So all these effects, you will not have it. This is just a concrete reinforced bunker that is standing there and is up to 8 meters high or 10 meters high. What you define it, it will have that effect. And it's extremely steep on the background, especially if you have a high resolution DTM. If you don't have a high resolution DTM, like 5 meters, or even with 2 meters, this is 1 meter here, you get a rounded shape. Because in the DTM, to calculate the steepness of the dam in the DEM, you take the position of one cell and the other one, and you interpolate between the two of them. So for some dams, in reality, they are a bit rounded, like here. But if it's a lower dam with a low resolution DEM, it's just a round bump where the rocks will fall over. So think about all those aspects if you want to integrate dams. If it's really like this, it's very high. I mean, you see that here. I know everybody knows the height of such a truck. If you stand next to it, 3 meters, 3.5. So you can guess what the dam is. I don't know how many cars fit in there, but we're talking about 12 to 15 meters, maybe 12. It's very steep, reinforced for sure. You see the layers. With such a dam, it might nicely work in your rockfall simulation. Also with 2 by 2 meters, because it's a bit more rounded than it is here. The slope is not so represented, but it will work. If it's a lower dam, higher resolution, lower resolution, you will have difficulties. Alternatives for doing that, you can use a net. Yes, you can. It would be an option. Or a thing we talk about since a long time, use a calculation screen, just collect the data and use another tool, a 2D tool for dam calculation, where you can precisely draw what the terrain looks like. With Frank Boyer in Grenoble, we've been talking a lot about that a long time, and we have it. We just didn't manage yet to make a tool out of it that you can run. It's now an Octave code. Yeah, and we still have to finalize that. We're not getting to it, so I'm just disappointing you here. I realize that, but that would be the best option. You used to be able to put your mouse here, draw a profile and plot, and there's an error. There's an error because we kicked out the mean and the 95 confidence interval energy output rasters. The mean and the confidence interval raster are assuming that energies are normally distributed. And when you look at simulations, individual simulations, and you look at distributions at points over the whole slope, you will see that energies are, in the best case, log normal distributed. So the natural logarithmic value of the energy, if you plot those in the distribution, you will see a normal-like distribution. That means that the CI was overestimating the energies. It was based, of course, on the 95% confidence interval in your normal distribution, which in extreme cases was higher than the maximum energy you simulated. And I saw that for a long time. And then we've been thinking about, can we output something that is based on the log normal? But then we have to explain what log normal is, and you have to, if you want that to use this distribution, you have to transfer or convert the log normal values, the log values back into normal values. And that's why we decided, now let's just kick it out because it's not correct, and use the simple 15, 90, 95 percentile values, which are correct. And if you want more information, you need to put a calculation screen. So that's the reason. But in the plot thing here, the plot was created with those mean and CI values. And since we kicked them out, I realized yesterday, because I never used that tool, that of course it cannot function anymore because the data underlying it is not there anymore. So that's hopefully an answer to the question before, why it doesn't function and what happened to the CI value. So use 95 percentile, that's more correct. Okay, so now we are 135 people left, quite a lot, really nice, thank you for being here. The floor is actually yours. Now it's the big wishing concert. What do you want to hear from me? What do I need to show you? Are there other wishes? What is not clear? Do some tests.
Could you show the profile, the plot, profile plot tool that it's on the bottom of the interface?
Yeah, it doesn't function for the moment since we don't have the 95 CI.
Okay, that's the one.
Yeah, but we will make it function again, but based on the 95 percentile energies and passing heights. Yeah. So this thing plots just your slope profile along the line you choose with your mouse, with then, as it in the old-fashioned 2D simulations, you know, with the heights, with the histogram, with the energies and the jumping heights as a line. Thank you. Is there another way to obtain more detailed values for jump heights, especially concerning the heights of protective structures? Is there another way to obtain more detailed values? Like what? Daniel, let's call ourselves by first name if everyone is okay with that. Daniel, can you explain your question, what you're looking for?
Can you hear me?
Yeah.
I used in past normally the CI for for the passing height now.
Yeah.
Because this was pure detailed.
No, the CI
Yes.
was based on
Ja, weil
I understand your
das
question.
andere ist nur mit ganzen Zahlen und das CI, wo
genau.
ist eben Kommastellen.
Ja, genau. Aber es war nicht genauer. So Daniel said it was more precise. Yeah, it was a, how to say it? It was a fake precision. If you really want, and maybe I switch to GIS, that can better help me to explain my answer. So we go to now this there. And now switch the whole thing to another screen. So I agree with you, Daniel, that now we have only these rough classes for the map.
Yes.
But the values which were differentiated spatially were based on the mean value plus twice the standard deviation observed in a cell, based on the assumption that the energies are distributed normally. So we gave you a very precise value, but it was just based on a mean value and a standard deviation in that cell, and then calculated the confidence interval, which was most of the time, as I said, more pessimistic than if you looked at the individual energies simulated in that cell. So if you really want to have for your protective structure the values, the real values, you should put a line there. You use a calculation screen. The thing I showed before, because that gives you the real distribution, the real percentiles that are also correct. So we use this map you see here. That is really to have an idea, where do I have the very high energies, the low energies. But if you talk about the protective structures, use a calculation screen. That's the way to go. Okay?
Okay.
Okay, there are lots of questions coming in. I just have to read them. If there is a building along the slope, how can I present it in the model? Using a net? Well, so Alessandro, if there's a building, indeed, what we do, if we're interested in what happens to those buildings, we put a net there, but not a real net. No, you're right. You can put a net with a given energy dissipation capacity and a given height, and then you're reproducing it better than if you use a digital surface model. You know, in the digital surface model, your houses are really in there, but then they're like concrete bunkers. A block is hitting it and will stop behind it. If it's if you have a good resolution. If you have a bigger resolution, the houses will be rounded and will just be bumps where the blocks go around it. So I think the net is the best one. If you have a high resolution, the digital surface model could function, but taking into account that still the houses will be a bit rounded and the rock cannot penetrate in a wall, which can happen in reality. Yeah, I think that question is answered. Are there heights still binned in classes? Yes, the energies and the heights. Here are the heights. There are classes. And if I remember correctly, because I don't, it's these one, 0.5 meter to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 10, 10 to 20, and more than 20. But the same answer as the question before. If you're interested in the real jump heights at a given location and energies, use the calculation screen. The rasters are for mapping. The lines are for having statistics on values for protective functions. Bum, 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 bum. Where are we? How is the friction calculated? Is it slope dependent or soil dependent? It's soil dependent. What do you mean with the friction, Patrick? Because I don't use a friction value. I use the soil type to calculate the resistance against penetration, which determines then the penetration depth. The friction is coming from the roughness, and the roughness together with the block is translated in a tangential energy loss coefficient, which is then, and there's a friction function using the roughness on the slope. So it's soil dependent and not, I think if I interpret correctly, your slope dependent means then slope steepness, or I hope I answered your question. You're going fast now. I hope I answered your question, Patrick. You have to use rapid to get the release areas used in simulation as new output dataset. Ah, okay. Yeah, can do. That's possible. Patrick is okay. Kjetil also okay. It's not with the number of release. Oh man, I have to write that one down because that's I just make a summary in my book. Proposition. I know it's findable in Teams afterwards, but there's so much. You can also ask your questions using the microphone. Just go ahead. It's good when I don't have to talk. All right. Yeah. So I have to go up again. Kjetil, that's, I hope I pronounced it correctly. Kjetil. That's doable. So if you want to simulate a structure instead of a net, we have to input increased values of energy. That's the next question I see there. Can you explain that? The user who, unknown user who wrote, so if you want to simulate a structure instead of a net, we have to input increased values of energy. Can you explain the question?
You hear me?
Yes, I hear you.
Good afternoon, first of all. I'm not a really efficient user of Rockyfor3D. That's my question is more basic, maybe. If, for example, you said before about the dam.
Yeah.
If, for example, we want to have a structure like a dam and not a net.
Yes.
From what I saw today or what I remember, we can't have an ASCII for concrete or something. So instead of that,
yes.
we can.
No, what I meant was you have two options for the moment, or three if you have another software that can calculate dams. So the first option is you integrate the dam in your digital terrain model. And then in the Rockyfor3D, it's considered as a reinforced concrete bunker because the terrain is fixed. It does not change in comparison to reality. As we said in the very beginning, if you look at the photos here in the chat, if a big rock impacts a dam or the ground, it completely changes the underground or it damages the dam. This will not happen. If you put a dam in the DTM, it's like a concrete bunker, okay? So it has unlimited energy dissipative capacities, and that is what's not realistic, and therefore we said an alternative could be to put a net there with a given height and a given energy capacity, 10,000 kilojoules or 12, whatever. And then you're probably a bit more realistic, a bit. It's not completely reproducing the effect of a dam, but that was what I wanted to explain. I hope that answers your question.
Yes, absolutely. Really, thank you.
Okay, thank you. Then we come to the next one. 3 dimensions are given as input for blocks. It sometimes doesn't match the volumes written in the log files. Yeah, I had this question once. And I think it has to do with rounding errors, indeed. But I can look at it again. Because we depending on how big the volume is, we calculate is it 0.05, then we need 2 decimals. If it's bigger than we get rid of the decimals, but I have to look into that again. It's a writing thing in the log file, but question noted. Thank you very much. In a place with unknown recent events, what do you consider is the best way to define the source cells, using a point, a line, or a surface automatically from the slope angle? Well, I would still then, unknown events, if it's the geological structure is relatively homogeneous. Relatively, they're always changing in the rock phase, but you see that everywhere in a limestone cliff there are some yellow spots. There's not a clear area where it's coming from, and the rest is competent climbing rock. Then I would use a surface, so really a polygon delimiting on the basis of the steepness, saying that is my start area. If you really know this is the event, it's coming from there, then of course you use a mini polygon or a point, yes. The line we use for regional studies, we did one for Graubünden, and then we did, in the end, I think it was 88 billion individual trajectories, and we could do so because we chose the upper parts of the cliffs. So we used not really a line, but we used a flow accumulation algorithm in GIS to define which are the upper cells in a cliff and only simulated from those. So a bit of the worst case. And that is corresponding to a line that you put on the top of a cliff. Voila. Eric, yeah, we tested 5.7. Does it exist? 5.7? Yeah, okay. On the same case, once we were surprised at such large differences. No, this is, the version 6 is much more optimistic. As I said, we changed also the rebound. So it's a combination of trees and the rebound algorithm. These are both. So I had some talks already with some engineering officers. They said, well, we tuned very often Rockyfor that it fitted, especially with the soil type. It doesn't change. You have to do this with the version 6. So probably there you can be more realistic or harder than you have been before to make sure that fits better your observations. So it's both. One suggestion, Mark, maybe go ahead, then
Yes.
you don't have to type.
Thank you
Go
very
ahead.
much. Among all interesting improvements, for us, the new option cliff area weighted for the start cell conditions fits our requirements for probability calculations very well when zoning. And we were wondering if you are planning to include an option to input directly the raster, a freely prepared raster with the number of simulations varying according to several considerations.
Some users might want to scream at you because they think, oh no, another option, more complicated. Yeah, I can put it on the list of wishes.
Yes,
What I
this is
do-
because
Yeah, I understand
we try to input the frequency,
course.
the frequency of occurrence, and it's varying
simulation.
according to several things if
Yeah.
rock mass varies and so on.
Exactly, I understand. What we do is, if you see the options that exist in the command line version, there are many, many more than the graphical user interface. For example, because Francois, he showed that nice picture in his article where the blocks are when they impact the trees. Say, well, that's a good way to verify if everything works correctly. So in the command line version, you can also get a lot of information on individual tree impacts. And this could be something for the command line version. So we keep the graphical user interface simple, and there it's a good option. So I'll just put it down like that.
Okay, thank you very much.
Yeah, thank you. Raster with in. Yep. Thanks. Other question. I know there are also people who are just beginning. Don't be shy with all those experts around. If you're trying today a bit now to do your first simulations and there's something not working, just ask me. I'm here till 17:30 in the extreme case. But if there are no questions, then, as we say in German, werden wir nicht künstlich verlängern. Lukas, is there any way to get the trajectories? Oh, yeah, you asked that. Good old question, coming back a lot. The philosophy has been always, if we start to give out individual trajectories as vectors, people will tend to focus on individual trajectories. And this goes a bit against the philosophy of Rockyfor3D, which combines physics with stochastics. And if you do stochastics, then you need to have a lot of simulations and you look at distributions of statistics of the variables in a cell. And so not to persuade people into selecting individual trajectories and really looking what does it do there, we always said, no, we're not going to do that. Now you said you use it for the overview simulations, and I think your question was a bit clearer, if I may say that, when you asked it the first time. No. Yeah, so this one it's probably not going to change very much. It's technically probably possible, but it also gives me the opportunity to talk with the example here on the 0.6 cubic meter and the silent witnesses. So we have this case, the block was here. You see it lying there. And now we made just 100 simulations and we have the probability of arriving here. And we compare that, and I'm going to use another group, the reach probability, with 500 simulations without forest. Here I am in a much more comfortable situation to interpret what are probabilities, what are energies, what are jump heights here. The problem is we have always in simulations, of course in the runout zone, where it becomes very thin, that we don't have a lot of trajectories to base our statistics on. So in the runout zone, we're always a bit thin with statistical interpretations. But if you want to have, like here, now going back to these other simulations without forest, 500. So here, this whole area is covered, and now we're really in these cells which are green. There was one trajectory coming through, so still there. I'm a bit thin on energies, but it shows me, okay, the probability is so low, I don't need it. But in here, there is quite some probability that a rock can come through here. So do sufficient simulations that statistically you're on the right side. And statistically, if you talk to statisticians, they talk always about 30 to 50 observations to have a real healthy statistic somewhere. So if you're in the runout zone, very far away, do sufficient simulations to come up with your conclusion. That's the thing I wanted to say. And as soon as we go to single trajectories, We're completely leaving that philosophy of making sure you have a rapid program that can create lots of numbers that you can interpret. Okay, but I understand why people want it, because then they can see if the program simulates this nice line and you can have all the statistics along it. But it will make the program slow, that's for sure. So that was a long response to Lucas. I hope since the model is more the question of Lucas in the manual with the outliers 1.5, it's a range, and we have to do a study now with the new version. We hope to do a publication then in the coming year on where, compared to the fresh documented blocks, where is this limit? Do you go to 1 or 1.1 or 1.2? No idea. We'll see. I cannot answer this question for now. We just put it safely at 1.1% generally as outliers, but it's up to you. According to your experience, question from Jacopo. Is there a minimal block size under which Rockyfor might not give correct simulation results? And the same in case for maximum block size. Yeah, good question. As shown by Francois, but also our own simulations in Evolen, the 300 cubic meter does seem to function. And I would say smaller than a human head doesn't really make sense to simulate. But also small blocks of 40 by 40 by 40 centimeter tend to reproduce what we observe in the terrain. So for now, my answer is I can write it down here, between 0.02, let's make it 3 and 300 cubic meters. If us does something in the next days, how could we communicate? Email, you found my email. Well, just if you type my name, Luc Dorian, in Google, you find my several emails. I spent a bit of time preparing this. I have to do my normal job. Next week I'm on holiday. If you don't expect an answer next week, no problem, but you can. And if you don't get an answer soon enough because it just disappears in the many emails I get, just call me. You find my number on the internet. Why you change this value? Okay, this was the answer of Lucas on the reach probability. Voila. So we have to wait for that publication. Okay, Damien, parfait. Yes, you're absolutely right. We have completely different situations. I think if you were happy with the results you had in terms of runout zone that you could confirm with silent witnesses, I would make sure that the runout zones are the same, but I would trust the energy values of the new version more. Okay, so that would be my answer there. So if the runout zone you feel comfortable with in terms of what you saw in the field with the silent witnesses, you go more for the energies of the new version. And I understand a lot that this creates sometimes difficult situations that I cannot solve. Often there's a deposit trench behind the dam. If you represent this by digging the dam, which soil type would you to mimic correctly the dumping capability of this structure? Ha! A 3, I would say. Soil type 3 in most cases. Or it's really soft, 2 meters deep, and then you use a 2. But yeah. Does this answer the question? Roel, if I pronounce it in the Dutch way, of Roel in Dutch. Would it be possible to link the different output rasters to allow filtering of results?
Yeah, maybe I should explain.
Yeah.
This is basically once you do the simulations, you evaluate with the silent witnesses, etc.
Yeah.
I can take out the
yes, got it.
The ones that I do like, but you can't filter the energy results, for instance.
No, you can't.
For these, because these these blocks which have too much energy, or
Yes.
this increases the value of, for instance, the 95 percentile energy.
Yes, it does. You
Is-
can only do
would
it
there be
with
a
the
way to
line.
filter it, or?
Yeah, you can only do it with the lines that I said. Look at the extremes in the lines, and then you can throw them out. That's the only way. Yeah.
With the energy lines, or?
No, with the with the analysis screens, you know, with the nets.
Ah, okay. Yeah, okay.
Yeah, that's the only way.
Okay.
Yeah. Yeah.
Okay.
I mean,
thank you.
if you do sufficient simulations, and you have 1% that are extremes that go really far, and you would use reach probability, and then a 95 percentile of energy, you're in the green zone. You're okay. You know, if it's for hazard mapping, and for, as I said before, if it's for dimensioning something, you really look at the individual observations in the calculation screens.
Yeah. Okay.
That would be the way to go. Yes, you're welcome. I have another. The speaker is unfortunately muted. Would it be possible to display the jump heights in 0.1 meter increments and present the whole numbers in the net log file? One sec. Now I don't remember. Are they small like that? I'm just questioned now by your question, Daniel. I'm looking into it. Don't I have it open there somewhere? No, bad. Open recent. Yeah, it's a bit more improvisation right now. I hope everyone understands that. Open. No. Okay, there. In the netlog file, Daniel, they are in 0.1 increment. They're not in whole numbers in the netlog file. There is the decimals, 1 decimal. Okay. I believe there are already more example plots in the new documentation. Okay, yeah, that was a good thing. That is a thing you can do as an association. But for now, there's not lots of feedback. There are lots of email questions, but would be great if we can, if you feel very confident about your mapping, if you send me pictures with the values you used, and so we can make a catalog on internet where you can see many examples of soil type and roughnesses. That would be great. Yeah. So also you can contribute to that. And I say this to everyone who's still here, 110 people. So if you send us emails with a picture and this is what I had as values, that helps everyone. Of course, if your philosophy in the engineering offices, we keep our things to ourselves, then don't. Okay, to continue, are large blocks deviating as much as smaller one when impacted tree stems? No, François, because they will, that energy will be so high that they will continue straight on. They will just go through the tree. And if there's tree destruction, there's no change of directory. Voila, yeah, you had the image in the chat. Don't I write that in the manual? If not, it should be there. So if there's more energy in the block than a tree can dissipate, which is often the case with a 200 cubic meter block, it will not change its trajectory at all. Okay. Lucas, which method of taking force is more realistic? Okay, the most realistic option is, firstly, it's a bit of a scientific work, but firstly, use tree detection with a 1 meter resolution normalized crown model, also difference, terrain, and surface model. And then you know where your gaps are, where there are no trees at all. Okay, so then you can make a forest map, forest, non-forest, which is really realistic. And then based on forest inventories, which you did in every significant plot that you have in every representative forest stand, you generate the missing trees that you didn't see in the tree detection. That is the most realistic options when it comes to number of stems and where they are and the diameters they have. It's also good to take some measurements on tree height, but that's really easy because you see it in the digital surface model. You can really sometimes see individual trees. You take, yeah, with steep surfaces, that is true. You take the tree height and you measure the diameter. So you have an idea how the height diameter relationship is. What remains difficult, I repeat myself, but since it's registered, I want to have it recorded. What remains difficult is the tree healthy? Is it really able to dissipate its maximum amount of energy? And thin and steep surfaces, yes, that is a problem. If it's really steep, you have bad quality. You don't see the individual summits of trees. That is true. Yeah, the net breaks, but not, and it's restored for the next simulation again. Yeah. So what happens? And this is a good question. I realize I didn't talk about that. Did we see it in the jump heights? So here we have the simulations. Here we have passing heights. Here we have our net. First question written there, if there's more energy than the net can dissipate, the flight parabola of the rock changes. It is as if you take energy out of the rock, and then the reduction of kinetic energy is equivalently reduced in the normal, in the tangential, and in the rotational component of the rock. This is not completely realistic, but it's an easy way to do it. So if the block has 1000 kilojoules and the net can dissipate 200, the block continues with 800 kilojoule kinetic energy for movement. That's all kinetic energy, pardon. And then because of that, and that is what reduced is 200 kilojoule is rationally diminished from all the three energy components. So normal, tangential, and rotational. That changes the parabola, and the rock continues with less energy, which is also in reality the case. Okay, now the next block that comes will encounter again a net that is installed. Okay, because we don't do the 100 or 1,000 simulations to create a reality that there are 100 blocks coming down a slope. No, we are creating 100 potential realities of a block coming from a single position. And we don't exactly know what reality looks like. So we do 100 possible events of that single event. And that's why the net is still intact and the trees are also intact again. Voila. So if you want to do that, you do a simulation. You see if your net is impacted with too much energy. You see that in the net file, and then you know this net will be destroyed. And if you have a multi-event block or multi-block event, your net will not hold. Okay, so that's two different things that we're comparing here. So now something, since you mentioned this, I get a lot of questions by people using a net, and then they're surprised that in the statistics of jump heights and energy below the net, that there's an increase in jump height and there's an increase in energies. Okay, those who have used this already and found the answer, really nice, very good. What happens, of course, if the net is for 80% of the trajectories functioning, so they're not flying over and they don't have too much energy for the net, they're stopped behind the net. Only the blocks that jump over or with high energy go through the nets continue. So the statistic that you see here in the raster below the net is only the statistic of the blocks that continue, which have the higher passing heights and have the higher energies. As a result, the statistics, the 90 percentile and all that, is higher below the net as above. I hope that's clear for everyone. You see an example here. Jump heights 1 to 2 meters says the statistic of the 95 percentile jump heights here, and below the net it's 2 to 5 meters. That's an exact effect of what I told before. We only have the statistics of those who jump over the net. So that was one I wanted to tell you. Are there further questions? Should tree trunks? Yeah. They're probably only, yes, they are. They're a bit like the lying trees. Some stumps of the trees are there for 10 years, so which is good in the first phase of a forest cut. And if you want to simulate that situation, you can say, okay, for the first 10 years that might be valid. And the only way is to put it in the MOH. But if you do so, if you calculate how many trees we have per hectare, it will probably never ever be more than in the 10% roughness, okay? Because otherwise you're overestimating how much roughness is there, or it is a very dense forest and trees are very small, so they don't dissipate any energy, and then you're overestimating the protective function of that. So mostly we leave them out. Are there more questions? If it remains silent.
Hi.
Hi. Okay.
Hi. I hope that the question is clear. Maybe I can send you an email if it's not clear. I tried to rerun some simulation made with the older version of Rocky4, and I've noticed that at the end of a slope, when a street begins made of asphalt, so a terrain type like 7. Okay, I've noticed that in a new version there is a drastic change in reach probability. That it has to go to 0 from a passage from a terrain type like a 3 or a 4 on the slope to a asphalted zone, terrain type 7, which in the older version tends to have some trajectory that seems to be
more
possible. Okay. And now with the new version, there is like it's like cut in the presence of the street of the terrain type 7. I hope it's not something that I did wrong in the simulation, but I use the same the same inputs.
Interesting.
Maybe I can
I fully understand your question. If you can send me the whole set of input rasters, that would be interesting.
Okay, thanks.
Because we didn't change anything in the soil, so you use 7, so the value didn't change. But with the new friction and scaling function, it could be that there is a stronger effect of that. But I have to look into that specific case.
Yeah, okay, so maybe we must reduce the number 7 to number 6 to I don't know, because we are working on it right now. So
all right, the streets are difficult. I introduced the number 7, saying, well, there's no roughness never on asphalt street, so I hope everyone puts 0, but I think most people do. And then we try to find what is the elasticity, or what is the value that corresponds to what we observe, and of course the different types of asphalt. And so we came up with this 7, which functioned okay with the old version. Maybe you're right. We should think about it's difficult to come up with the good one. I don't have the good one like that. I need cases where rocks jumped over streets that we mapped well, and see if we can reproduce it and tune it like that. But for the moment, I don't have a good value. But I'm happy to look at it.
Okay, thank you.
Thank you. I only have a dam with 1 meter cells. I recommend to go to 2x2, yes, because I have the feeling, but I just started testing it. I have the feeling with 2x2, it's a more realistic runout zone, and it's less precise, pretending that we can predict that 1 meter that the rock is coming through here and not through here. So there I'm always careful. So I use I always do it in Saga, but there are some experts here. I know they are in QGIS. With the processing tools, you can also use resample of Saga tools or from Grass, or maybe there's even one of QGIS. If not, I have the possibility to use a 5x. Now I would use 2x2. 5x5. I haven't tested one with the new version, but I'm curious to see if we have too long runout zones. Are the difference between version 6 and 5 particularly important when the trajectories are particularly long with steep slopes, even if the forest is not taking into account in both cases? Ooh, no, I have seen the differences on short slopes and on long slopes, both. So difficult for me to answer your question, particularly which one, the bigger and smaller. Difficult to see. I had the longer version in Tesh where they the runout length was more or less the same, but the energies, of course, were different, and also the reach probabilities. So for now, I saw them in both. Okay. I encountered issues with simulation involving source zones. Yeah. Yes. No, there's no solution for that other than simulating if you want to have the reach probability precisely for a given source area, you should you should calculate them separately. But the way it's done right now is mathematically correct. If you have two cliff areas above each other and all the rocks go over the second, you have a correct value. But as soon as some rocks are deposited above the second one and some continue, you have a very high number of source cells and a lower number of passengers below. So you get lower reach probabilities, you get these jumps in it. So it's correctly what you see, it's correctly calculated. The solution is only to separately simulate cliffs. Because the fragmentation of the not included is placed. Ha! Yeah, it's Oriol. There was an exchange with University of UPC in Barcelona, Catalonia, to work on fragmentation, and they have published some papers on it. It never resulted in a module or something, or an option in Rockyfor3D. The thing is, as far as I know, also from publication, what you can do is predict how the rock is going to fragment and how many smaller and bigger parts. So we always end up with the question, okay, how are we going to do it? We have one big rock. We can calculate at an impact how much force is coming on the ground, but also then on the block. And giving a certain force, there's fragmentation according to a given distribution. And from that point, do we simulate all the individual parts? That is what reality shows. I think it would be a difficult enterprise. So yes, in our heads, it's considered for development. The realistic answer is don't expect in the coming 4 years that, but maybe there are surprises. And now, because of this, we will think about